think we're live. Okay, so sorry today, no egg drop. No egg drop. Not enough kids here today. Bummer. So 3, 26, 21. So our objective today is to talk about the number E. Now E is a number, which seems crazy. It really is. The number E is actually in my calculator. It's right there, okay? There's an E. And the number E is like pi. You know how pi just goes on forever and ever? The number E is like pi, and there it is. E is about a 2.718281828, blah, 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 okay? So the number E is approximately 2.71828, blah, 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 okay? But it's like pi. It never ends. It never repeats. It's an irrational number. Any number that goes on and on and on and never repeats is called an irrational. Pi, square root numbers are irrational numbers too. Now, where do we get the number E? Well, the number E comes from this formula. So if I were to take values and plug them in for x into both spots, like for instance, this one would be like a 1 plus 1 over 100 to the 100th power, you'd think that you'd get a really big number, wouldn't you, to the 100th power? Wouldn't you think so? But it turns out, since it's such a small decimal, let's go parentheses 1 plus 1 divided by 100 to the 100th power. It's about a 2.7, okay? All right? And then if I get bigger values like 1 million, so if I go and plug in 1 million in for x, and I'd have a 1 plus 1 over 1 million, 1, 2, 3, 4, 5, 6, to the 1, 2, 3, 4, 5, 6. If I go parentheses 1 plus 1 divided by 1 million, 1, 2, 3, 4, 5, 6, to the 1, 2, 3, 4, 5, 6. You'd think, again, to the millionth power, you'd think it'd be a gigantic number, but nope. And you see it's getting closer and closer to what we said E was, right? And then if you take a billion and do the same thing with a billion, you go 1 plus 1 divided by 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, to the 1, 2, 3, 4, 5, 6, 7, 8, 9. It just gets getting closer and closer to that number E. So back to that number E, okay, let's compare. Oh, Claire, I want that. To that number E, okay, let's check out E. Look how close these are, right? Pretty darn close. So the larger the values of this value of x, the closer it gets to this value of E. Now, what if it was infinity, which is impossible? So you say we approach infinity because you can't get to it. So this is a calculus. This is a calculus terminology. The limit. The limit means get closer. You can't get there. You cannot get to infinity. Does that make sense? But the limit says get closer and closer, approach it. So if you had 1 plus 1 over infinity to the infinity power, you get the number E, okay? Now, it's called the number E because of this guy named, and it's not Euler. This is French. He's a French dude. His name is Euler. His name is Euler. I don't speak French, but this is pronounced Euler. And he was the dude that came up with the number E, and that's why it's called the number E, because it's named after Rene Euler, okay? So there it is. The number E is named after this guy, and it's pronounced like this, Euler, but it's really looks like Euler's number, but it's French, okay? So the number E is this definition, which is about 2.718. Now, why is it such a big deal? Because with the number E describes continuous growth or decay. Has anybody taken AP Bio yet, or AP Chemistry? You guys, anybody, any of you guys? You'll see this number. You'll see this number in higher science classes because it makes sense. If it talks about continuous growth, continuous decay, then you're talking about bacteria, right? Or half-life like a radioactive material, things that will grow exponentially, they continuously grow, continuously, right? And that's the rate at which things grow continuously. So now this one, same thing. If you go 1 minus 1 over infinity to the infinity, and if I use a really big number, let's say something like, I'll take a billion. First, let's try a big number. So if I did a 1 minus a 1 over a billion, 1, 2, 3, 4, 5, 6, 7, 8, 9, to the 1 billionth power, 3, 4, 5, 6, 7, 8, 9. It should be similar, right? The only difference is the minus. So let's find out what that is. So this number is, I'll go parentheses and I'll go 1 subtract 1 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. And I get this number, okay, about 0.3678. But that turns out to be e to the negative 1. In fact, I'll show you. If we go and we go e to the negative 1 power, e to the negative 1 power. There it is, okay? So this definition is going to be e to the negative 1. Okay, now, this is going to describe, e to the x is going to describe growth as long as x is positive, and this is going to describe decay as long as x is negative. Okay, so if x is positive, we'll have exponential growth, and if x is negative, we'll have exponential decay. All right, let me show you. So if I had, for instance, y equals clear that. If I go e to the x power, okay, back up. All right, let's graph this. Right, exponential growth. You see it, right? And then if I did e to the negative x, exponential decay. But the cool part is it is exponentially decaying continuously, which is what happens. Like, okay, here we are in COVID, right? This is what we want COVID to do, correct? And it would do it hopefully continuously as a population. We hit herd immunity. It's continuously happening, right? Okay, so let's turn the page. So E is kind of an important thing, okay? So example 1, here we go. A virus grows continuously at a rate of 4% per hour, exponentially. There's the beginning population of 10,000 virus, okay? Write a continuous exponential function. So let's write this down. Let's write y equals a e to the rt. Or we can go a of t for time is equal to p e rt. Same equation. One's in function notation and the other's in just regular, okay? Same equation, okay? So, this is an exponential equation because the exponents up here, right? My r is a rate, 4%. My a is my beginning amount, right? 10,000, right? And then I get a cycle of time, which is my percentage. So let's see if we can set this up. So in this equation, I can go y equals 10,000, because that's my beginning population, e to the 0.04 t. 0.04 because 4%, right? 0.04. We just move the decimal 2 places. Everybody good on that, right? That's just percentages, okay? Now, how many are present after 8 hours? So this thing's growing at 4%, right? So, and this is in terms of hours, right? Rate per hour. So if I plug in 8 for t, we should find out how many are in our experiment. So we're going to go y equals 10,000 e to the 0.04 times 8. Okay, so then, all right, if you don't have a good calculator, you can always borrow mine, right? So the E button that we want is down by the 4. You guys see it? See it there in blue, e to the x? That's the button we want. So I'm going to go 10,000. I'm going to go e to the 0.04 times 8, right? And it grew to about 13,771 bacteria. Now I'm going to round it because if it's bacteria or a virus, then I'm just going to rewrite it. I'm not going to round it. 13,771, not point, but that's in terms of my virus cells. Actually, viruses aren't cells, are they? Right? They're not a cell. Isn't that weird? Viruses are not a cell.
Excuse this interruption. Can we please have all sophomores who have not registered or pre-registered yet, please head down to the wrestling room with your computer. All sophomores who have not pre-registered, please head down to the wrestling room with your computer. Thank you.
Okay, example 2, banking. So in banking, it's the same thing. When you either get a banking account or a credit card, they're charging you interest all the time, right? In theory, right? So a credit card company will charge a daily rate of 1.5%. If your balance is 12,000, write an exponential function to model this. Well, daily is pretty close to continuous. Agree that if they're going to charge you every day, we can say that's just basically continuous, okay? So I'm going to say my y equals my 12,000, my e to my 0.015 to the t power, okay? So I'm just going to plug in 10. I'll go y equals 12,000 e to the 0.015 times 10. And I'm going to use my calculator. I'm just going to go 12,000. Use my E button. 0.015 times 10. And I get about $13,942, okay? And 1 penny, okay? So if you don't charge it, you just leave it in there, you don't do anything with it, you basically are going to have to pay an extra $2,000, right? It's almost $14,000. And so this one's pretty much the exact same formula, so I'm not even going to do that one. I could do this by the day, and I decided not to, so continuously and daily are the same thing, okay? You don't get much difference. Okay, so that's all I have. Not too bad. Okay, and if you want to work on your egg drop, you can, or homework, you can.